So, moving on, 1920, Stern and Gerlach, electrons have spin. Okay, that was a magnetic discovery thing, looking at magnetic fields. And spin is related to angular momentum. Okay, and angular momentum is also conserved. Okay, so that figures in here. And then in 1925, Wolfgang Pauli comes up with the exclusion principle, originally for electrons and electron spin, but ultimately is extended to all fermions, spin 1/2 particles, and dealing with the idea of not sharing the same quantum state at the same time. And of course, he gets the Nobel Prize for this in 1925. Keep in mind, Pauli also becomes one of the major arbiters on things related to quantum theory. That people in the late 20s are constantly communicating with Pauli about quantum ideas because he's considered one of the experts, okay? Even though he was only born in the same year that quantum theory was developed. But he grew up with it, so he was really good at it. Okay. So again, prior to 19, I don't know how much of this you can read, okay? But it says radiations from radioactive substances, Cambridge University, 1930. And the first name listed, Sir Ernest Rutherford. Not a surprise, okay? By this time, Rutherford had been appointed director of Cavendish Lab, had many things to put under his name. No question about that. Second one, James Chadwick. Anybody know Chadwick is famous for?
Neutron.
The neutron, right, discovers the neutron, okay? And then the third name, C.D. Ellis. Who can tell me who C.D. Ellis was? Exactly, and up until about 6 months ago, I didn't know who he was either, okay? But he turns out to be one of those major players that never gets much press, okay? He had an important role to play in this. Okay, Ellis began studying beta and gamma radiation in 1920. A little background on Ellis. He had originally gone to the military academy in Great Britain, and he was planning on becoming a military engineer. That was 1913. In 1914, he had the summer off, so he decided to take a tour across Europe. And what happened in the summer of 1914? World War I, exactly. He was in Germany in World War I. He was interned in Germany. Now, coincidentally, Chadwick was also in Germany at the time, okay? He had studied with Rutherford when Rutherford moved to Manchester University around somewhere in the 1910s. So he had been a student of Rutherford. Apparently he had met Geiger because Geiger is now on his own in Berlin, and he was studying with Geiger, okay? But he's also interned. And these two guys wind up in the same place. And they're able to get some equipment and do some experiments in photochemical reactions. And Ellis got the bug. So when the war was over, he went back to Great Britain, he transferred to Cambridge, and he got his degree in 1920. Chadwick also went back to Britain. By this time, as I said, Rutherford had become the director of Cavendish Labs, and he brings Chadwick in to do his PhD work and also as an assistant. Ultimately, he winds up being the assistant director of the lab. Chadwick says, hey, I met this guy in Germany. Maybe we should bring him in. So that's how Ellis gets sucked into this. And Rutherford and Chadwick decide they're going to work on the alpha particles because that's the big thing. And they give Ellis the job of looking at beta decay, which was a very good move in the long run. Okay, so in 1927, Ellis and another researcher, Wooster, come up with a lead-walled calorimeter, which seems a little odd, but you're dealing with radiation, and lead stops radiation, so keep everything in and maybe start making some decent measurements. So they showed the total energy deposited corresponding to the average energy of the beta spectrum, so you smooth out that curve, okay, they're getting it, but it's only about 40% of what was being expected from the mass defect. So either energy is not conserved or something else is carrying the energy away. In 1929, Meitner and Orthman confirmed the result. And small footnote, Bohr is still saying, wait a minute, on average, energy is not conserved. Okay? And of course, Bohr was an authority. 1928, Dirac comes up with an equation that predicts the positron. And I'm sure you're all familiar with that, so I won't go into any great detail there. And he wins the Nobel Prize in 1933. Positron, the first antimatter particle, and also kind of a key player in neutrinos, as we'll see. And then back to Pauli, who is a major player in all this. Okay. Now, the 20s had been good in some respects for Pauli, but a downer in other respects. Yes, he had done Nobel quality work early on, was in line for a prize, but in 1927 his mother died by suicide, kind of a downer. 1928, his father remarried to what Pauli referred to as the evil stepmother. Okay. Guess he didn't care much for her. But Pauli was also appointed to a professorship in Zurich. So he goes to Zurich, and lo and behold, he runs into Kathy Deppner. Okay? Kathy Deppner was a cabaret dancer that he had known in Berlin. Okay? And they reacquainted, one thing led to another, and Pauli says, let's get married. And Kathy agrees with one condition. She's also having a romantic relationship with a chemist. And she says, I will marry you, but I will continue to have my liaison with the chemist. So Pauli says, okay. So we married her. As you might expect, this does not end well. Okay? So in 1930, they're divorced. Pauli was 30. And Pauli's comment about this was, if it had been a bullfighter with someone like that, I could not have competed, but such an average chemist. So, where else are we going here? Oh, I had that in there. No. Now, what did Pauli know in 1930? Okay? So, he knew there was this conservation of energy problem. Okay? That was a big deal. He knew that there was also a conservation of angular momentum problem associated with spin. Nitrogen, 14 protons, 7 electrons, remember the model at the time, okay? So that's 21 spin 1/2 particles giving you a net spin of 1/2. But the measured spin of nitrogen 14 is 1. That's a big problem. That suggests that either something's wrong or conservation of momentum, angular momentum doesn't hold. He was also aware of a conservation of linear momentum situation, okay? And what we got up there is a cloud chamber track. I tried to find a better one than that, but that's the best one I could find. That we talked about with alpha decay, the particles go like that. Well, with beta decay, the beta may come off like that, but the recoil on the nucleus may be like that. They are not online. That much they could tell from the cloud chambers, but nobody actually was able to measure the momentum until the 40s, and then yes, it comes out that the momentum of the beta did not equal the momentum of the daughter nucleus. But it was just kind of a peripheral thing there. I read some instances where it kind of said, oh yeah, they knew all these things, you know, there were 4 violations of conservation laws. Well, yeah, sort of, but the 4th one wasn't known yet, and these 2 were a little iffy. The big one was the energy problem.
Do you have any idea how they measure spin? Like, how do you measure spin in
As I understand, it has to do with magnetic measurements. That the spin gives you a certain. I have no idea exactly how that's done either. It's a good question. Oh, I should also say, I forgot to do the disclaimer. I am not an expert on neutrinos. Okay? I have never formally studied neutrinos, nor have I studied quantum mechanics or particle physics or detectors. But I have developed some expertise over the years, particularly through QuarkNet, and just to give a boost to Jillian's ad, if you got a chance to do a QuarkNet workshop, do it. It's a lot of fun, and you get a lot of good stuff from it. Okay, so 1930, Pauli comes up with his desperate remedy, okay? Dear radioactive ladies and gentlemen, this was an open letter he wrote to the participants of a conference that was going on 8 days after his divorce was finalized. Now you might think he didn't attend this conference because he was a little down about the divorce. Not exactly. He was involved in planning a ball which was going to be one of the major social events of Zurich for the season. And it took place the same week as the conference, so he wasn't at the conference. But he did want to get some ideas across, and that's how he did it. He sent this letter, and he proposed another particle in the nucleus. Neutral particle that he called the neutron, mass about that of an electron, spin 1/2, obeys the exclusion principle, speed less than speed of light. Anybody afraid of confusion with the neutron we know? When was the neutron discovered?
32.
32, very good. Okay, so the neutron hadn't been discovered yet, so the name was still available. Okay, so that's why he called it a neutron. Ultimately, that has to be changed, but that's what he said. And during beta, you'd get one of these neutrons of his coming off with an electron. Total energy was constant that way because you had another particle in the mix to carry away the other energy, and the fraction of the mass defect would be split between the two. Now, he wasn't ready to publish this. This was just kind of the germ of an idea, but he wanted to get out there and see what other people thought. So, positives and negatives. Well, it solved the energy problem. Okay, that was neat. It solved the nuclear spin problem. Okay, because now he's putting in another particle for each of the electrons in there, so now you got an even number of particles in there, so you wind up with spin 0 or spin 1. So it works out. Okay, that's good. But how to detect the particle? Okay, all of the particle detectors at that point used the charged nature of the particle to detect it. You know, whether we're talking about Geiger counters, or photographic film, or spark chambers, or cloud chambers, you needed a charge. So that was going to be a problem. And many of his colleagues said, well, this is nice, the mathematics is good, it seems to fit, but what good is it? So Pauli told his friend Walter Bade, who was an astronomer, I've done a terrible thing today, something which no theoretical physicist should ever do. I have suggested something that can never be verified experimentally. Okay? And Bade said, okay, I'm going to bet you a case of champagne that it gets discovered at some point. Okay, so Pauli took the bet. Pauli took the bet. 1931. Now, I should also say, Pauli was feeling the effects of things that were happening, the negative things that were happening. He was beginning to have some depression. It might not have been the best thing to do, but he went on a lecture tour in the United States, and he talked about this hypothetical particle he was proposing. In late 1931, he's back in Europe, in Italy, at a conference organized by Enrico Fermi. The two of them talk about the particle. Fermi likes the idea, and he starts thinking about it seriously. Bohr still says beta decay energy is not conserved, or it's only conserved statistically, thinking about that. And Pauli is now suffering from deep depression, so he seeks help from Carl Jung, the psychologist. Jung matches him up with one of his psychotherapists in training, happens to be a young woman, did great things for Pauli and brings him out of the depression. He and Jung remain friends for the rest of his life. Okay, so 1932, here we are with Chadwick and the neutron. We know, yes?
Sorry, Harry. Going back to the point about the energy spectrum. So, and maybe this is known, but I'm just curious. For the beta decay had the spectrum of energy, which was weird.
Right.
But what he was proposing is that the neutrino has its own spectrum of energy. So between the neutrino and the beta, that then energy is conserved.
Yeah. Basically, one would be a mirror image of the other, so that everything would flatten out. Yes, exactly.
Thank you.
Exactly. Okay. So Chadwick discovers the neutron, alpha bombardment of beryllium. You get a free neutron out of that. Happens to be the reaction they used to set off the plutonium bomb in World War II to get the free neutron to start the chain reaction. This is when it comes out, February 1932. Nucleus has protons and neutrons, no electrons. Nobel Prize, 1935. And it solved the nitrogen-14 spin problem because there's no electrons there now. So you got, in the nitrogen, 7 neutrons, 7 protons. Again, even number of spin 1/2 particles, so 1 or 0 over the possible results. But Pauli says there is another problem involving spin 1/2 particles. That if you look at what's going on, a neutron is decaying into a proton and an electron. Okay? So, typical beta decay, there's a change. Spin 1/2 neutron, spin 1/2 proton, spin 1/2 electron. Okay, now you got 1 or 0 again on the right side. So that's a problem. So you need another particle to deal with that. 1932 August, Carl Anderson detects the positron in a cosmic ray shower. So this is a photograph. You've got a lead plate there, and this is the track of the positron. Okay, coming in this way, curving that way. There was a magnetic field in there to produce the curve, and slowing down the particle results in a bigger curve on the other side, bigger curvature, I should say. And so that validated Dirac, and this is the first antimatter particle, Nobel Prize 1936. Notice that with most of these things, we're seeing this pattern that it doesn't take too long for people to get recognized for these discoveries, especially these particle discoveries. And the Nobel Prize comes pretty quickly after that. Okay, the 1933 Solvay Conference in Brussels. Solvay conferences started in 1911. They were called in irregular periods of time to discuss an open question in physics and or chemistry. This one was devoted to nuclear structure. Irene and Frederick Joliot-Curie. Irene Curie was the daughter of Pierre and Marie and went into the family business, so to speak, in terms of dealing with radiation. And they had produced the first artificial radioactive isotopes, alpha bombardment of different nuclei. Okay? They also found a new form of beta decay, okay? Positron emission from a radioactive nucleus. Hadn't been noticed before. Remember, Anderson did it with cosmic rays. Okay, so this is the first time we see it in a decay situation. And they had a little hard luck because they had done a number of experiments, and in their data, there was evidence for the neutron and there was evidence for the positron before either Chadwick or Anderson, but they didn't see it. Don't feel too bad. They got the Nobel Prize in Chemistry in 1935 for this stuff up here. Okay, so they were presenting their results. Okay. Also at the 7th Solvay Conference, Charles Ellis from the Cavendish lab before, and his student, Lynn Henderson, were testing Bohr's hypothesis. Okay, Bohr's hypothesis said the energy spectrum should tail off at high energies but have no upper limit, that this should keep going. So instead of that curve coming back down to the horizontal axis, it should go asymptotic. That was Bohr's prediction. Well, Ellis showed there is an upper limit, and it does correspond to the mass defect situation. That you can't get more out of it than the mass defect of the reaction. And the average energy that he's getting was below that limit. So energy's lost, or there's another particle. There has to be something else involved. Many physicists then and now believe that Ellis and Henderson discovered the neutrino. And by the standards in place today, the indirect measurements that were made, they would have been considered the discoverers of the neutrino at that point. Bohr did not give up his theory for another 3 years. Okay, so Bohr was really invested in that. He never really published a huge amount on it. Papers were apparently circulated because, he sent one to Pauli, who wasn't really keen on it. But he hung on to that for a good long time. Okay, Enrico Fermi. Fermi, of course, famous for his work on the Manhattan Project later on. At this time, he had been appointed to professor at a university in Rome. 24. What did you do when you were 24? He gathered a group of 6 young scientists referred to as the Via Panisperna boys. Via Panisperna was the name of the street where their institute was located. Okay? And there were some heavy hitters in that group, as we'll see. He had spoken to Pauli in 31 about Pauli's particle. And in 1932, he began calling it the neutrino, Italian for little neutral one. Usually, most books give Fermi credit for that, but apparently, one of the boys Amaldi came up with the term, and Fermi liked it, so he kept using it, okay? And he was also at the 33 Solvay conference. And after that conference, he went home and he started to really put his mind to the neutrino. So in December, he came up with a complete quantum theory for beta decay. All of Pauli's ideas and all the new information he had gotten at the conference assumes the electron and neutrino could appear spontaneously, also guessed they were related, which we now know to be true, but he was just guessing at that point. And the mass was small or zero, okay? Protons and neutrons could exchange identities. And of course, this is all stuff we know about beta decay now, and all the known conservation laws held. Okay, so it's pretty good. Also, he used the theory to derive the shape of the graph. Okay, that's a big plus, okay? Being able to derive something straightforward, not just explain it, but actually be able to show that that's the way it ought to be. And the model was the first rough weak theory. He didn't actually mention the weak force, but he laid the ground for what became the weak force, and probably the first modern field theory. Now, you figure this is going to be a big deal, okay? So he goes to a major publication, Nature magazine, and submits it, okay? And what happens? Speculation's too remote to be of interest to the reader, okay? Kick in the teeth. 50 years later, the editors admitted this may have been the biggest editorial blunder they ever made. And no argument with that. So, Fermi has to go somewhere else. At the time, Mussolini required that any paper that an Italian wrote for publication, wherever they got it published, also had to be published in an Italian journal. So, one of these three publications was an Italian journal. So that people would read it, he published it in a German magazine, German journal. And nobody says what the third journal was, but there was a third one out there too. But anyway, people read it, and that was the important thing. Okay. Now, one of the key things has to do with this idea of inverse beta decay, and we will keep coming back to that. Fermi's theory said beta decay could run in reverse. So, neutron goes to a proton. Now, I didn't realize it when I stole this graphic. That bar is not an antiparticle bar, that's a negative sign, okay? This bar is an antiparticle, okay?
Wow.
Otherwise it gets very confusing. Okay? Down here not so bad because they use a plus sign, but up there. So what happens is you flip the neutrino to the other side, the neutron plus the neutrino would give you a proton plus an electron. Okay? But that means you can induce the reaction. That by colliding a neutrino with that neutron, you can make the reaction happen. And similarly, an antineutrino with a proton could induce the emission of a positron. Okay. That makes detection possible. If you can find the products, then you can see what's going on there. Okay, that can be detected. Now, Rudolf Perls and Hans Bethe, a few months after the publication, did some computations, said it's not going to happen very often, okay? Neutrinos would traverse 1,000 light years of water without interacting. So it probably wouldn't be detectable, okay? That was their conclusion. They were, of course, working with beta decay energies, okay, which were not that big compared to some of the other things. So ultimately they would be proved wrong, but at the time the information was, yeah, it isn't going to work. Okay, so a little bit about Fermi after the neutrino.
Aaron,
Yeah.
you said colliding a proton with a neutrino. How do you get a neutrino to collide with a proton?
Patience.
Patience.
Okay, so the neutrino model cemented his reputation as a theorist. I know my impression of Fermi was always as an experimentalist. I didn't realize how much theory he'd actually done, more like fermions. That was a theory thing too. So this was a big deal in terms of cementing his reputation. But he didn't think it was going anywhere. So he and the boys started bombarding all the known elements with slow neutrons and producing radioisotopes. This is the work that he wins the Nobel Prize for in 1938. Now, just a brief aside on this. In 1934, they did an experiment that probably resulted in a fission. He was bombarding all the known elements. Along the lines, they bombarded low neutrons onto uranium, and of course there'd be some uranium-235 in it. Okay. They didn't realize it was fission. They misidentified the products. Okay, so they were better physicists than they were chemists. Okay? But one can only speculate on what would have happened if fascist Italy, with the minds that they had to work with, had come across the idea of nuclear fission in 1934. How might World War II have turned out differently? Interesting thing to think about. Okay, Fermi goes to Stockholm to get the Nobel Prize, and after that, he and his family go to the USA. Fermi's wife was Jewish. Italy was fascist. They were starting to carry the same things that the Germans were in terms of the Jews are at fault, so he decided to get out. He was not the only one who decided to get out. There were a lot of European expatriates who went to the United States in this time to get away from fascism. And of course, 1940s, he worked on the Manhattan Project. Okay, 1937. Anderson again and Seth Niedermeyer detect the muon. They did it in cosmic rays again. And this is a particle with a mass between that of a proton and an electron. Shortly before this, a Japanese theorist by the name of Yukawa was hypothesizing a strong force interaction particle, exchange particle, that he called meson. That's what they thought they had because it was in the right range. It was originally the mu meson, but when they found out it wasn't a meson, they just dropped that part of it and called it the muon. Seth Niedermeyer also had another claim to fame in the Manhattan Project. He was the one that came up with the idea of imploding the plutonium to make it produce a chain reaction. So he's a pretty smart guy too. Okay, now, Ettore Majorana, the Grand Inquisitor, okay? He was one of the Via Panispermicals. Now everybody in that group had some kind of nickname. And they sort of fancied themselves along the lines of a religious order. So Fermi was the Pope. Franco Rossetti, who was Fermi's right-hand man, was the Cardinal Vicar. And Majorana was the Grand Inquisitor because he was the sharpest one at criticizing. He could take somebody's idea and pick it apart in a nice way, but tell you what was wrong with it. Okay? He's a very bright guy. He was also described as wealthy, bored, bemused, and unconventional. Okay? He had originally studied to be an engineer, and Emilio Segre, one of the other boys, who ultimately wins a Nobel Prize for discovering the antiproton, convinces him you'd have more fun in physics. So he became a physics guy, and over a 10-year period, he managed to publish 9 papers. Several of them were somewhat influential. He was not big on writing papers. I mentioned that the Curies, the Joliot-Curies, had data that supported the neutron. He noticed that before Chadwick published. He told Fermi. Fermi said, well, write a paper. Couldn't be bothered. Okay? Couldn't be bothered. Didn't really matter to him. In 1937, he messed around with the Dirac equation. He comes up with the suggestion that maybe the neutrino is its own antiparticle. Okay, interesting thought. In 1938, he withdrew a large sum of money, boarded a ship, and was never heard from again. This was sort of became the Italian version of Where's Waldo? That this went on through the newspapers and whatnot for about another 15 years. That sightings were reported in Italy and in other parts of the world, and it was like, where is Ettore? Nobody knows. One suggestion was he committed suicide. His family never bought that because he was Roman Catholic and he was very religious. So the idea of him taking his own life didn't seem reasonable to his family. Along the same line, somebody said, well, maybe he went into a monastery. But even if they kept that secret, you'd figure at some point it would have come out, you know, maybe after he died, that he'd been there. So that never came out. The smart money was, because he had a lot of money, he went to South America, changed his name, and lived quietly ever after. Because nobody ever heard of him again.